There we go. Okay, now I want to know what kind of convergence this series has. If you do nothing to it, right, you leave it exactly as it is, I can see that as an alternating series, right? It's got -1 to the n over square root of n. And I can prove to you that that series converges by the alternating series test, right? So I could prove to you that it decreases and its limit is 0, right? That's the proof. Now, when I say make everybody positive, which is what you do when you want to look at absolute convergent, that's what you got. Now, all I'm doing is removing that, or making it 1, if you like. This series, everybody is positive. This series, if you wrote it down, for instance, if you write down n equals 1, you get -1 over the square root of 1 plus +1 over the square root of 2, -1 square root of 3 plus 1 square root of 4, plus and minus forever, right? That's what makes that an alternating series. Now, if you remove the -1 to the n, you'll get 1 over the square root of 1 plus 1 over the square root of 2 plus 1 over the square root of 3. The only difference between the untouched one, right, the original question and this one, is that these are now all positive terms. Are you cool with that bit?
Yeah.
Right, now, we know that this series converges because you can prove it converges by using the alternating series test. If I rewrite this guy as 1 over n to the half, can you see that it's a p series?
Yes.
And
less
the
than
p,
1.
so it diverges.
Yes.
And we have a name for series that have this. If the original converges, but when you make everybody positive, the new series diverges, we call them conditionally, too many T's there, conditionally convergent. So that would be your answer to what does this original series do? It's a conditionally convergent one. Now, if you tried the ratio test, all you get is 1. And 1 is inconclusive, which means the ratio test is no good. It doesn't tell you if it converges or if it diverges.
Okay. So you have to use the alternating series test.
You have to, for this series, you can't do the ratio test because if you try to do the ratio test, the result is inconclusive. Like,
Okay.
we don't know.
All right, I learned a lot. Thanks.
Okay. You find that when you do some series, the ratio test isn't any good to you. That's an example of one. Right.
Okay. Thank you.
All right. So we'll be. Is this everybody here already? Oh, time flies when you're enjoying yourself. I need some more caffeine in me, so here goes.
Mix a little scotch in there and you got something.
Yeah, well, that's true, but I'm not. I think the college frowns upon us being drunk in our job. You know, it's not like the military where you can get drunk and drive jets and command submarines, right? I think they're much more flexible. Okay. Well, good evening, everyone. Let's us get started. We are going to be looking at what's called a power series, and we're going to be focusing on essentially what is a power series. That's the first thing we're going to be doing. And then the second thing we're going to do is we're going to find, I guess that's the best word, the values of x where a power series converges. And we call that interval of x's, because it will be like all the x's from 0 to 10 or -2 to +2. We call that range of x's the interval of convergence. So we're going to find the IOC, the interval of convergence. And we're also going to find another thing called the radius of convergence. And typically the radius of convergence, it's a single number, right? And we pretty much every textbook I've ever seen call it capital R. And an example of that might be capital R equals 3. And so the interval of convergence will look something like all the values of x from -1 to +1.
So
You can use x as -1, but you can't use 1.
I was
And R is 1.
I was just about to ask, Professor. It's -1 all the way up to, but not including 1.
Correct.
Okay.
In this particular example. Now, lots of power series, there are infinite number of them, are pretty boring and don't get used much, but there are a subgroup of power series which are really useful, and we won't focus on them in this section, but we will in the one that comes after that, which you'll have to wait until next week to see what that guy is. Are really useful, because what they allow us to do is to find a new way of describing functions, and we'll use power series to do that. So let's start off with what is a power series. Power series is an infinite polynomial written in the form sigma n equals 0 to infinity an x to the n. So if I plug n equals 0, you get a to the 0 x to 0, and then a1 x plus a2 x squared plus a3 x cubed for eternity. So what we're doing is we are creating a function. Let's call it f of x. And this function is being written as a power series, as an infinite polynomial using sigma notation. An example of that might be, for instance, this one. That is an example of a power series. The guys that we're calling en, this guy here, is essentially that fella, right? The 3 to the n squared, right? Anything that has an n in it but is not x to the power of n, that's this piece. And then x to the n. If I plug n equals 0 in here, I will get 3 to the 0, x to the 0, and I don't like that guy, so I'm going to change it, pretend it says n squared plus 1, so I can get 1 there. So it's going to be 0 squared plus 1. And then you get 3 to the 1, x to the 1 over 1 squared plus 1. And then you would get 3 squared x squared or 2 squared plus 1 forever. Okay, let's find out what these are if you tidy them up. What number is 3 to the 0? 1.
1.
And isn't x to the 0 1?
Yes.
And 0 squared is 0, but 0 squared plus 1 is 1. The net effect is that that guy happens to just be 1. This guy is 3x over 2. This guy is 9x squared over 5. And then so many x cubed, so many x to the 5s forever. So that's what a power series is. It's an infinite polynomial, typically written in this very generic way, as various multiples of powers of x. So far, so good. So what would we like to know? Well, not all power series are created equal. This one here, for instance, for certain values of x, right? Like x equals 2, right? X equals -1, x equals 5, right? For various values of x, when I plug it into that series, the series converges for some values of x, but not all of them, right? If I, for instance, plugged in, I don't know, 5, x is 5. If you calculated that as 3 to the n, 5 to the n over n squared plus 1, you would discover that the thing actually diverges. So we are only interested in the values of x of a power series that converge, right? We don't want to know, well, if you plug in 82, it diverges, because that's no use to it. It's not very interesting, right? What is interesting is, oh, if you plug in x is 2, it converges, or x equals -1, it converges. We're interested in that. So how do we find all the places where a power series converge? Well, we calculate what's called the interval of convergence. So to find the interval of convergence of a power series and r, which is the radius of convergence, we typically use the ratio test. +90% of questions where you're being asked to find the interval of convergence and the radius of convergence are, the ratio test will do the job, at least at the beginning, right? That's the first thing you'll do. And you'll see you have a little tweak at the end where you have to find out, okay, then what about the two endpoints? See, in this case here, it converged at -1, right? But it didn't converge at 1, right? So you could use -1 and get an answer, but you couldn't use 1. How do we find out whether the endpoints work or don't work? So that's like the second phase. So the first phase is use the ratio test to get the initial interval of convergence. And then in the second phase, test the endpoints. The endpoints in this case would be -1 and 1. Test the endpoints to see if they converge. So it's a process. That's the good part. You do pretty much the same thing every time. On the negative side, it's a long process. These are not typically going to be, unless you're really lucky, a quick question, right? It's going to take a fair amount of work from start to finish. So since I created this one, let's do that as our first example. So let's assume that this question was, find the radius and interval conversion of this power series. We start by using the ratio test to get the initial interval of convergence. So that's the absolute value of an plus 1 over an. Now, in this particular guy, this one here, an is the whole package, including the x's. And an plus 1 is what you get if you turn all the n's into n plus 1s. Are you comfortable about what an and an plus 1 are? Right, we've done ratio tests before. Okay, so let's see what we get. It's going to be the limit as n tends to infinity of 3 to the n plus 1 x to the n plus 1 over n plus 1 squared add 1 divided by 3 to the n x to the n over n squared plus 1. Now, typically, I wouldn't write this like. What I would normally do is jump to the next line. And that is top fraction times the reciprocal of the bottom one. Are you comfortable with going from here to here without needing to write this line? If you need this line, I guess you should write it, but isn't that basically top guy times reciprocal of the other guy? So far, so good. Now, you cancel everything in sight. Okay. Well, there's quite a few things that can cancel. That 3 to the n will cancel with that 3 to the n plus 1 and leave me with 3. That x to the n plus 1 will cancel out with that x to the n, and that will leave me x. And then, once you've cancelled everything that you are capable of cancelling, you write down what's left. And I'm going to write it by changing the order a little bit. And that guy in the bottom, can you imagine me foiling it out and adding 1 to it to get that? So that's where we are right now, right? We've cancelled everybody and we're at this stage here. The next part of the process is you separate out the pieces that have anything to do with n's, and you leave behind the other piece, which is typically going to only have x's or x's and numbers in it, right? So in this case, that guy. So this is equivalent to that. Imagine the x is on the top. Well, you know, you can put it at the side because it has the same effect. Now what you do, I want to find out what the limit, I guess I can keep that bit, of this is equal to. And you see it's 3n squared plus 3 over n squared plus 2n plus 2, right? That guy. What would the limit of 3n squared plus 3 over n squared plus 2n plus 2 get? So if you find the limit of this fraction, what number would it be? While you're thinking about it, I'll put another line in. What number would this be? Someone's put it in the chat. See? No, just someone saying hello. Okay.
Aren't you going to divide by n squared?
Yep. And if you do, what will your answer be?
You're going to have 3/1.
Yeah, so it's 3.
Yeah.
So what you end up with is 3 absolute value of x. Now, were you thinking I was asking something else? I was just asking that, right? Nothing with frills on it, just basically what is the limit of this fraction equal to? Now, you could also have found the answer by doing L'Hopital a couple of times and you would have got 3, right? So if that bit's 3 absolute values of x. So all we've done right now is find out what the limit of the ratio as n tends to infinity is. And it ends up being that guy. According to the ratio test, what number must the limit be less than for convergence to happen?
1.
Agreed? We're almost at the point of being able to tell the values of x where this power series converges. For that to happen, this thing needs to be less than 1. Great. So what is the absolute value of x going to be less than if 3 absolute x's are less than 1? Again, it's not meant to be a trick question. What would you do if I said to you 3x is less than 1? Wouldn't you divide both sides by 3?
Yeah.
So what 1x would be less than what?
1/3.
1/3. Yeah. Now, if you're looking at that, what you're looking at is actually the interval of convergence. The interval of convergence is the values of x where this power series will converge. That is only going to happen if the absolute value of x is less than 1/3. That is values of x from -1/3 to 1/3. Right? If you take the absolute value of any number in that range, so I'll put a little 0 there. You imagine up to 1/3 and over here to -1/3. As long as you're in this range and you take the absolute value of it, it will be less than 1/3. If you try and pick a number where my finger is like 1, it'll be too big. If you try and pick a number like -2, it won't work either. So we have found the interval of convergence. And that's phase 1. And phase 1 is use the ratio test, which we've done, to get the initial interval of convergence. Now, phase 2 says we now have to test the endpoints. The reason for that is that this guy could be a lot of different possibilities. It could be that you can use the 2 endpoints, in which case that would be the completed interval of convergence. It might be that you could use x as -3, but you couldn't use x as +3. So that would be the final interval of convergence. Or it could be that you can't use the first value of x, but you can use +1/3, right? And of course, that's the initial one where you can't use any of the endpoints. So one of these 4 versions is going to be the final phase 2 interval of convergence. Oh, and by the way, I haven't done R. This power series, we say that its center is 0. Do you notice that the distance from the center at 0 to the final endpoints, that distance is 1/3, which is that number there. So the radius of convergence is how far away from the center can you go to reach the ends of the convergence interval. So let's kick in with phase 2 now. And phase 2 is test the endpoints. First one I'm going to test is x is -1/3. The power series that we're going to test it on is this one. If you plug -1/3 into this fella, you get 3e to the n times -1/3 to the n over n squared plus 1. You need to simplify as much as possible. So here's my next step. -1/3 to the n can be split into -1 to the n over 3 to the n divided by n squared plus 1. I can now cancel these two, and we will be left with n equals 0 to infinity, -1 to the n over n squared plus 1. So do you see, when you're finished, you'll be left with a power series that we've been dealing with in the last 2 weeks. That power series. Now, if that power series converges, it means you can use -1/3. If that power series diverges, you cannot use -1/3, right? So that's how we're going to tell if I can use it to do a square bracket or whether it's a curved bracket. Now, you don't know what you're going to get until you get there, but you have 10 tests that you could use. Well, actually, you've got 8 tests that you can use. You can't use the ratio test anymore, because if you try to do it, you just get 1. So of all the other tests, not the ratio test or the nth root test, that's the 2 I'm kicking out. Of all the ones that are left, what kind of test would work with this series?
Your AST.
Right. Okay, alternating series test. Now, I don't have as much time as I'd like. Can you trust me that if you use the alternating series test, which would probably take another 5 minutes, that this series converges? Now, I can talk you through it. If this is an alternating series test, wouldn't the guy be 1 over n squared plus 1? I can prove that that's decreasing, and I can prove that its limit is 0, therefore it converges, right? That's essentially what I'm doing. Now, that means that x equals -1/3 is a usable value. And I'll put a little circle around that to remind me. Right. Now we'll return and we'll test the other point, which is 1/3. And the power series that we're going to test it on is the original one.
If I test one point, do I have to test the other point using the
Yeah.
same?
Yeah,
Okay.
because one of them might converge as this one did, but this one might not, right? It might, but there's no guarantees.
But does it matter if I use a to the n or a to the n plus 1 on either?
I would always use a to the n just because the math is easier.
Okay.
So what we're doing is essentially the original question, right? Which is the AN one's the original, right? So we have that guy. Don't know if we need this, but is that guy. Those two cancel out, and 1 to the power of n is really just 1, because 1 squared or 1 cubed, it's still 1. So we are left with that guy. And it's not the same as the other one, right? It's close, but it's not the same. The alternating series test wouldn't work on that one, right? It's not an alternating series, right? And remember, you can't use the ratio or the nth root test. They're never going to get used in this part of the puzzle. What test because there's a couple could you use for this one.
Can't you just use brute, like just throw infinity in there?
Well, if you're doing that, you're testing the series. You're testing the sequence, but not the series.
Okay.
So brute force doesn't get used as any of the tests, except technically the divergence test. But if you plug in infinity here, you get 0. And the divergence test doesn't work, right? If the answer's 0, you don't know if it works or it's convergent or not. What of all the other tests? So we'll throw the divergence out for this time. What of all the other tests that are left would work on this one? I can think of 2. No, change my mind. I can think of 3 tests that could work. One over n squared plus 1. What kind of test might answer, is that a convergent or not? You could do a limit comparison test to 1 over n squared. I actually think you can get away with just a straightforward comparison test to 1 over n squared. You could also do an integral test using that guy. I would never do that unless I was forced to. If you use a limit comparison test or a comparison test, this series converges. And again, you're just going to have to take my word for it, but it does. And why does it converge? Isn't 1 over n squared a p series and p equals 2, and that's bigger than 1, so it converges. And since I'm using the same in the limit comparison and the comparison, you know, I'm getting the same result, right? It converges. This one, if you eventually proved it, would be the inverse tan. Then you could do brute force, and you would get that it adds up to pi upon 2, which means it converges. So no matter what test you use, you'll get the same result. That means we now know, try to keep to the same vocabulary, that x equals 1/3 is a usable value. Now, our original interval of convergence was -1/3 to +1/3. We've tested the endpoints, and so our final interval of convergence is that you are allowed to use both endpoints. Now, the radius of convergence is 1/3, and it's never going to be anything different, right? It's always 1/3. Once you've got a radius convergence, you're good. Right, does that kind of stand up to what I said as these are extremely long questions, right? You got a ratio test to get to this guy. You got to do 2 tests on the endpoints, and all of that leads to just one little result, the interval of convergence and the radius of convergence. Are we good? Right. I want you to use this process as like your template for every single power series question, because the only thing that's going to change is what these guys look like, but the process will not change. You might have to tweak it a little, but it won't change. So let's jump and show you some nice quick versions. By that I mean special situations where you don't need to do anywhere near as much work, right? So here's one. Sigma n equals 1 to infinity, 2 to the n, x to the n over n factorial, right? There's a power series. And we are going to find the radius and interval of convergence. The limit as n tends to infinity of the ratio. So we're doing the ratio test. To speed things up, I'm going to plug in n plus 1 and then just multiply by the reciprocal where we use ends. That saves us having to write, oh God, where is it? That saves me having to write that guy first and then do it, right? That just basically improves the efficiency of the process. In these questions, you never lose your absolute values. They stay there all the way through. Right, now, is there anything on the top that you can cancel within the bottom? Is there anything here on the top? Anybody here cancels with anybody in the bottom?
And
Go for it. Calvin.
I was going to say the n factorial.
Okay, now n factorial will cancel n plus 1 factorial. You know, that's, yeah, if you've seen enough of them, you get used to it, right? Won't n plus 1 be left on the bottom? You comfortable with that?
Yeah.
Right? You've seen enough factorials cancelling. John, were you going to pick the same one, or are you going to tell me a different one?
No, I was gonna say 2 to the n.
Mm-hmm.
It just leaves two at the top.
Agreed. If we cancel the x to the n plus 1 and x to the n, don't we leave an x in the top? And there's no significance to the colours here. I just happened to have a red pen in my hand at the time. And now we move into essentially all the bits that don't have x and x, right? You kind of split them. Now, in this question, we're trying to find the limit as n tends to infinity of the fraction 2 over n plus 1. Couldn't you do that just by brute force, just by plugging in infinity, right? And if you plug in infinity, isn't 2 over infinity 0? So what do you get? You get 0 times the absolute value of x. But wait a minute, 0 times that guy, all of them are going to give me 0. So are you comfortable that this particular one, the limit is 0? And it doesn't matter what value x is, right? If x is 7, isn't 0 times 7 still 0? And if it's a billion, 0 times a billion, it's still 0. And that's quite a cool version, because isn't 0 less than 1? And according to the ratio test, the series will converge. Not only will it converge, since it doesn't matter what value of x you use, it's going to converge. It means it will converge for values of x, any value of x, minus infinity to infinity. So we now know the interval of convergence. Negative infinity to plus infinity. In other words, every value of x works. What will the R value be for this question? So if you merge
Infinity
it,
squared. No, I don't know.
just infinity, just infinity. So if you go either side of 0, because that's where the center is, right? R is infinite. We go with that. Do you notice that question was a lot quicker because of that? Because I don't need to test endpoints, right? Because infinity is everybody. And so our workload has been reduced. You kind of hope that you get a lot of questions that look like this one compared to the one I did at the start, because, you know, workload. Now that was a special case, right? And by that I just mean you got an interesting, easy to deal with answer. Let's show you the other special case, which is also interesting because it reduces your workload. And before I do that, if you have a power series that's written like this, if x is 0, it's guaranteed to converge. And you might say, well, how do I know it's guaranteed to converge? Won't all of these guys here be, well, who knows, 5 times nothing, 4 million times nothing, 3/4 times nothing? Won't they all be zeros? And so x equals 0 is guaranteed to be a solution to any power series. So if you take a general power series, there are three situations. The interval of convergence could be, you know, an interval like that. And there could be square brackets on either side. The interval of convergence could be everybody. And lastly, it's a bit weird to call it that. The interval of convergence could be just one value of x. It only converges when x equals 0. But that's not how we write it down. How we write it down is a little curly bracket with 0 in it. The next question I'm going to do is one where the interval of convergence is only 0, right? X equals 0 is the only one that works, because that works no matter whatever the series is, right? It's going to work.
The
So,
negative 1/2 to 1/2, isn't that?
yeah, I just made that up.
Okay, that's not going to be squares. It's going to be circles.
It could be.
Okay.
It could be that guy.
Yeah, that's what I thought.
And all the other combinations. I just don't want to mess the thing up by writing down 4 guys. The gist of it is that it's a start and a finish number, right?
Okay, sorry.
No, yeah. So other people will probably think the same thing, John, right? So it's a start and finish number, or it's everybody, or it's only 0, right? That's kind of the 3 choices. So let's show you one where this is the solution. So sigma n equals 1 to infinity n factorial x to the n over 5 to the n. So we'll do the limit as n tends to infinity. We'll do the ratio test. So it's the limit as n tends to infinity. Okay, an plus 1. So n plus 1 factorial x to the n plus 1, 5 to the n plus 1. Turn me upside down, 5n, n factorial x to the n. You now have the limit as n tends to infinity. Okay, let's see what we get when we cancel. Can't we cancel the factorials? And this time, n plus 1 is left on the top. What else can cancel?
The 5.
Okay, so 5 to the n cancels with 5 to n plus 1. Wouldn't you get left with a 5 in the bottom?
Yep.
Anything else to cancel?
The xn plus 1 and the xn.
And what's going to be left when you do that one?
Just 1.
1x, and where
Yeah.
will it go? Top or bottom?
Top.
So if we put all the pieces that are left, and there's not much, we have an n plus 1 and a 5 and an x, right? Now, if you make n go infinite here, right, this fraction, if you make n infinite, you can do essentially brute force. Infinity plus 1, infinity divided by 5. But wait a minute, infinity divided by 5 is still infinity. And is infinity times a number, just treat absolute value of x as a number, isn't it still infinite? So essentially, doesn't this mean it doesn't matter who x is, theoretically at least, it diverges? Except when x is 0. Because infinity times 0 could work, right? You could get an answer. And x equals 0 is guaranteed to work in a power series. So we don't need to test that. We just need to assume that it's usable. So that means our interval of convergence is a single value of x, 0. Because the ratio is infinite, right? Nobody converges, well, isn't infinite bigger than 1, right? So nobody converges. What would the radius of convergence be if the interval of convergence is 0?
Is
When
it
this was
undefined?
no, it's a number. So in this case here, it was infinity. I haven't got the other guy handy, but yeah, if it was this up here, it would be a half. If it was this one, it would be infinity. So what would it be in this last situation?
Must be 0.
Must be 0. Because if you start at 0 and that's all you've got, doesn't that mean you don't go any further left or right? You go 0 distance. So yeah, that question was much quicker than the first one as well. So when you're doing power series, you're kind of hoping that everybody works or nobody except 0 works, because the reason you were hoping for that is much less work, right? Can get the answer a lot quicker. You won't know until you do a question which one is it going to be, numbers, everybody, or just 0, right? You won't know which of these you get until you kind of try out the question. So let's pick one. This is question 2. And we're being asked to find the interval and radius of convergence of -1 to the n, x to the n over the square of n. So start off, as we do with every question, by using the ratio test. So it's going to be the limit as n tends to infinity of, make everybody n plus 1, and then turn everybody upside down like that. So that bit is essentially an plus 1, and this bit is 1 over a to the n plus 1 turned upside down. Now, let's show you what happens in this one. X to the n plus 1 cancels the x to the n, and we're left with an x on the top. And to special about that. This might catch you a little bit. See this -1 to the n plus 1? It cancels out this -1 to the n. Now, theoretically, doesn't that mean that there's a -1 left on the top? A single. But if you take the absolute value of -1, doesn't that just turn into +1? And that has no effect on the answer, right? It's just like saying 1x or just saying x. So essentially what you should do in these questions that involve -1 to the n's, or who knows, -1 to the 2n plus 1, whatever it happens to have here, the trick is basically to realize that they don't matter, right? They cancel each other out, and anything that's left just going to turn into a 1 anyway. So ignore them. And that's as good as we can do right now. So I'm going to do the limit as n tends to infinity. I have a square root of n over the square root of n plus 1, and an absolute value of x. We need to find out what that guy is equal to. Whatever it is, right, whatever this is, I'm going to be sticking that guy next to it, right? He's going to still be there. Square root of n over the square, it's the whole thing, the square root of n plus 1. You could probably tell by looking at that what the answer is going to be. Can you tell?
Well, if you put in infinity, you're gonna have infinity over infinity, right?
Yeah, that's probably not a good idea, right? Because you can't really tell what that's going to be. You could do this. Let's do it to the side. Different question. Oh, you might be thinking what I'm doing. Different question, but kind of similar. Suppose I had that. Then couldn't I divide the top and bottom by n? And I'd be looking at the limit as n tends to infinity of 1 over 1 plus 1 over n. And then I could do the brute force thing. Right? That would work. Now, this guy here, although it might look different, in lots of ways, it's really isn't that different.
Well, can't you put the be like the big square root and then the n over n plus 1 in one big square root?
You are exactly on form, John. That's exactly what you do.
Okay.
Now, you can either look at that guy and say, oh, wait a minute, that's 1. So the answer is the square root of 1, which is still 1. Right? If you don't see that, you are allowed to do this. Right? If you want to see it more formally. To me, getting to that point, I can tell, oh, that's going to be 1, so it's the square root of 1. But if you want to do it this way, that's going to be 1. Right, no matter how you look at it or how you cut it, that's 1. So what you're left with, oh, well, technically, all you've got is that guy. And that needs to be less than 1 for convergence. Because according to the ratio test, the limit of the ratio, which is this guy, must be less than 1 for convergence. So I know what my initial phase 1 interval of convergence is. It's all the values of x that have the property that their absolute value is less than 1. So that's all the numbers from -1 to 1. And I know the radius of convergence is 1. So far, so good. Now, the next bit just takes time. Don't we have to test each endpoint? Because it might be I can use -1. It might be I can only use 1. It might be I can't use any of them, and that happens, that's fine. Let's see what happens. I'm going to test the endpoint. So I'm going to test x is -1 first. Here is my power series. And I'm going to replace that x with -1.
Square root of -1 is going to be a problem, right?
Oh, well, that's an n, so it won't matter. The only x is the x on the top. The square root of n.
Okay.
Yeah, if it was the square root of x in the bottom, I would be really
So
worried as well.
you plug the value into x. Okay, I'm sorry.
Yes, into x.
Sense.
Now, you gotta tidy things up if you're going to try and find whether they converge or not. And sometimes you have to tidy up some weird looking stuff. This here, -1 to the n times another -1 to the n. What in the heck does that equal? Well, let me tell you the answer and then try and prove it to you. It's 1. Not 1 to the n, because 1 to the n is 1, right? So it's 1. And let's see if I can prove it to you. There's a number of different approaches. All of them lead to the same result. If I do -1 to the n times -1 to the n, the rules of algebra says that if you multiply two things together, you add the powers. So far, so good. Now, that is -1 to 2n. Now, doesn't that mean it's -1 to an even number? Because n's 1, 2, 3, 4. So it's going to be -1 squared, -1, 4, -1 to the 6. So using that logic, I could say it's 1. I could, however, approach this slightly differently. See this guy here? I could call it -1 squared raised to the power of n. That is equivalent to that. And -1 squared is 1, and 1 to the n is still 1, right? So whatever way you convince yourself, do you notice that the answer is 1? So there's our guy. Now, to save time, I'm not doing this formally. You would have to in an exam question. We're simply just going to talk it through. Do you recognize what kind of test we could use on this very simple series, 1 over the square root of n? What's that stand for, John? P-series, yes. P-series test. If you write it as a P-series, isn't the square root of half and that means it's less than 1. And what do you get for P series is less than 1? You get a diverger. So that means can't use me. Well, maybe we'll get lucky with the other endpoint. Maybe it will converge when x equals 1. Well, you have n equals 1 to infinity, -1 to the xn over the square root of n. Get n equals 1 to infinity, -1 to the n times 1 to the n all over the square root of n. So far, so good. Now, 1 to the power of n. Isn't that always going to be the number 1, right? 1 squared, 1 cubed. So really, the simplified or the simplest version of that series is this guy. What test could you use on that guy? And remember, ratio tests aren't allowed, right? So what test could you use on this series?
Go with the alternating series test.
I would. And can you trust me that it converges eventually? You'll find that. Well, that means, yep, you can use me. So to finish this question, the final value for the interval of convergence is you cannot use 1, but you can't, -1, but you can use 1. Do you see the square bracket on this side? And of course, R doesn't change. Isn't this question very similar to the first one we did, right? Where we had an interval of values and we had to test the 2 endpoints. And in this case, one of them failed, but the other one worked, right? Can you imagine a situation where both fail? Well, if that was the case, wouldn't the answer just stay put? It would look just like that guy, right? Back in home. Any questions? I'm going to do a lot of these, or as many as we have time for. Is there any questions you're not sure about and then you want to ask? Okay, let's
I don't have questions right now, but when I start doing the homework, I'm sure I'm gonna have questions.
right. Well, shoot me emails. I'll try my best. It's probably going to be you'll have issues with just the mechanics, right? The things that you end up getting might be quite ugly, and trying to find out what the limit is n tends to infinity might not be always that clear. I'm trying to see something a little bit interesting. This is 5. There are a lot of different flavors to what a power series looks like. It's the math changes depending on the situation. So for instance, do you notice this one isn't even a fraction? It's still a power series, but it's not, you know, the typical guy over square root of n, right? It doesn't look like a fraction. Doesn't change a darn thing. It's the same basic process. It's going to be the limit as n tends to infinity of an plus 1 over an. You can handle that. It's going to be the limit as n tends to infinity. Right, an plus 1 is this guy. And on the bottom, an is that guy. Right? That's all. Right, we've got a fraction. Let's go cancelling. Let's go hunting. Anybody top and bottom that you can see cancelling? Anybody from the top and the bottom that can cancel?
The 8.
Okay. If you cancel this with this, an 8's left behind. And if you cancel this with this, an x is left behind. So we are now looking at the limit as n tends to infinity of 8. And I'm going to FOIL that guy out. So it's n squared plus 2n plus 1 all over n squared with an x. Right? Now, if you've done enough polynomials in your world, you kind of get used to what something is because you just see so many of them. If you look at this guy, do you see why the answer is going to be 8? Why that limit is going to be 8?
Yeah, because it's going to be 8 times 1.
Right? Agreed? So 8 times 1, 8. I don't know why I put an absolute value around 8. It's a positive number. So you end up with this guy. So that is the limit of the ratio. For it to converge, it must be less than 1. We did that in every question. But to get the interval and eventually radius of convergence, don't we need to know what the absolute value of x is less than, not what a absolute value is less than. So in this case, I will divide both sides by 8, just like you could do in a normal inequality. So the absolute value of x is less than 8, 1/8. So I know the radius is that guy, and I know that our initial interval of convergence is that guy. Are you comfortable about values of x that make that true are always in this interval? To give you an idea, suppose the value of x, right, the absolute value of x is less than k, where k is anything in the universe, any number in the universe. That's what the interval of convergence would look like. Do you see the pattern? Right, if that's 20, this is minus 20 to 20. If that's 4, minus 4 to 4. In this case, it's an eighth, minus 1/8 to plus 1/8. Do you see what's going on there? That's, if you can write it like this, you should be able to convert it into an interval pretty much automatically, right? And it's always going to be less than, right? You're never going to have anything greater than, for instance. So we have initial interval of convergence is that. Now going to test the endpoints. One of them is -1/8. And so let's see what that gets us. N equals 1 to infinity. 8 to the n squared, x to the n. N equals 1 to infinity. 8 to the n squared, -1/8 to the n. And to find whether a series converges or not, you very often have a lot of tidying up to do. This guy is going to become -1 to the power of n over 8 to the n. So I basically took that fraction and gave the top one the negative and the bottom one the 8. And if I do it that way, these two guys cancel. And what we are looking at is that. Does that series converge or diverge? -1 to the n squared, converge or diverge? Any takers? That's the key. Isn't this getting infinitely big? In other words, if I use the divergence test on this, or I use the alternating series test, can you trust me that when you're finished, it diverges? And to speed up, if I did 1/8, can you trust me that you would end up with n equals 1 to infinity, basically just n squared. And that also diverges. So you can't use me and you can't use me. So you're finished. The interval of convergence is the same interval that you started with because none of the endpoints are usable. and we're done. Every test that we have in the books could one day be used in this process here. But it seems to me at least, isn't the alternating series and the P series two of the most common ones that pop up? Right. So if you're looking at a series and you're thinking, how am I going to test if it converges or not? You might want to look into a power series, a P series, I should say, or an alternating series, and get your answer that way. Do you want to see another one of these X to the N versions, or can we move on to the next version of a power series, which is ones that are not centered at 0? So do you want to see another one of the ones we've just done, or can I move on?
I'm good with moving on if everybody else is.
Okay, I'm getting feedback. If you're not, you would tell me, right, guys? I'm looking at the chat in case you can't voice communicate with me. Right, so none of you, that's good news.
I'm all good.
Right, so you're going to find out as you do them what the problems are, right? Because we haven't covered every permutation in the universe. We couldn't. So what we're going to look now is a power series centered at x equals a, and they look like this: n equals 0 to infinity, a to the n, x minus a to the n. That's the only difference. You don't have an x to the n, you have an x minus a. So an example of that: 2 to the n, x minus 3 to the n over n cubed. Right? When you have a power series that doesn't have an x to the n, but has an x plus 4, x minus 3, x plus 7, you are looking at a power series where the central interval, right, the place where the middle of the interval of convergence is no longer at 0, right? So it's not 0, add a half, take away half. It's going to be 3, add a half, take away half, right? Or whatever the add and take away number is. So let's do some practice at finding the center.
If you were to graph this, would you be able to physically explain the convergence and divergence by looking at the graph?
If you graph this for various values of x, it would look something like this. Right, let's look at the center, that's 3, and let's just pretend that the radius of convergence was 2. So right in the middle, x is 3. And as long as you only go to either side, so what would that take me to? 5 and to 1. Then my interval would be from 1 to 5, right? Now, if you graphed it from x equals 1, 2, 3, 4, 5, the function would have a continuous set of values, right? So if I plugged in 1.1, it converts to this number. If I plugged in 3, it would converge to that number, right? So along here is the value of x that you would plug in, and it would convert to a normal number. So you'd have a piece of the curve which would look nice and pretty. But if you tried to pick a value of x outside of the interval, right, like over here at 6 or over here at 0, the answer diverges, which means it's infinite. So the function is nice, and then everybody outside disappears. Technically, they're up here, or I guess it could be down here, right? But they're at infinity, right? Not usable, right? And if I tell you the answer to a series is infinity, it's not really telling you anything except that it's huge and has no final value, right? It goes on forever. So
if what you're saying is true, then everything that converges lands on the curve.
Yes.
So essentially, you're basically finding all the terms on the curve for that interval.
Yes.
Okay, that's cool.
That's a good way of looking at it. Yes. And the pieces that are not in the interval of convergence, they're not there. Technically, they're floating away up at some theoretical place called infinity, right? But that's no use to you, right? We in mathematics, we don't think of that as being actually a place, right? I can't plot 0, infinity, right? It's not a point. So a power series has essentially only one feature that makes it different when they're centered at A compared to these, and these ones are centered at 0. Now, x equals 0 doesn't mean I'm plugging x equals 0. I'm just saying it's centered at 0, right? So let's try this guy. And you're going to be asked the exact same questions. What's its interval and what's its radius of convergence? Now, I just made these numbers up, by the way, so we're actually going to find the real numbers. So sigma n equals 0 to infinity, 2 to the n, x minus 3 to the n over n cubed, right? We use a ratio test. And we try and find out what the limit of the ratio equals, and that will help us to decide when convergence will happen. So it's going to be the limit as n tends to infinity. Plug everybody here, replace them by n plus 1s. And then turn them upside down and replace them by n's. Now, pretty much the next stage is very similar to previous questions, right? We're into cancel me time, right? This guy gets cancelled by that guy. Any volunteers? Tell me something in the top that cancels with something in the bottom.
The 2n and the 2 plus the 2n plus 1.
And we agree a 2 left at the top. Right, while I've got your attention, Natalie, you tell me another thing that cancels. There's one more thing that can cancel.
Is it the things that are cubed?
Not those guys, but these guys. So what would happen if you cancelled those two? X minus 3 to the n cancelling with x minus 3 to the n plus 1. They would cancel, right? Well, what would be left?
And x minus 3?
Yeah, on the top. So what we've now got is a limit as n tends to infinity over an n cubed and n plus 1 cubed, a 2, and that guy, right? That's all the pieces that are left. That guy gets separated from everyone else. Now, you see this thing here? The absolute value doesn't matter because, you know, whatever that is, it's going to just be a positive number when you're finished, if it's a number at all. But we need to find out what this is equal to. And there are different ways to do it. I wouldn't suggest this way, but sometimes, you know, you have to do what you have to do. If you take n plus 1 cubed and you FOIL it all out, can you trust me you get that? Right? So n plus 1 times n plus 1 times another n plus 1, that's what you would get. Just trust me on that. Now, can you see the guy in the top and the guy in the bottom? What would the limit be in this question? What would the limit of that guy divided by that guy give me? Right, I could do L'Hopital. I could divide the top by n cubed. What would I get? We've done enough powers over powers to kind of see what's going on here. If I cover them up, does it help any? What number would that ratio be? Last chance? Yeah, 2. So it's going to be 2 absolute value of x minus 3. Now, if you want to see a different approach to getting the limit, if you take the limit as n tends to infinity of 2n cubed over n plus 1 cubed, you could rewrite it as the limit as n tends to infinity of 2 lots of n over n plus 1 cubed, basically turning them into a fraction. Isn't that guy going to be 1? So you get 2 times 1 cubed. There you go, you get 2 again, right? Different way of getting to it.
Yeah, I like that way though. It really makes sense to do that.
Yeah,
It's
and
not
that's what you should do.
backwards.
Yeah, when you look at how do I get an answer, you should always say, you should always pick the one that method makes sense to me, because if it makes sense to you, you're probably going to do it right, and you're probably going to remember to do it. Right. Now, so that guy's 2. Now, according to the ratio test, doesn't that need to be less than 1 to converge? So I'm not changing any of the rules. That's what we did all the other times. Now, you don't want 2 lots of something less than 1. We want that guy on his own. So how about less than a half, right? So divide both sides by 2. And this is kind of where the process kind of looks like it diverges, bad choice of word, that it's different from the other one. But it's not that different. Okay, so in this question here, how do we solve this inequality? How do we find what values of x this is true for? Well, I don't know if you've seen an absolute inequation before, but this is what they become. That guy in the middle is sandwiched between this number and the negative of this number. So what we've got here is a rather weird looking inequality with 3 pieces to it instead of the typical 2 pieces, right? That's normally what you get, 2 pieces. But once you get over that weirdness, it's actually not difficult to solve. And we're going to use the same rule that I've used in many situations in algebra. It used to be called, as long as you do it to both sides, it's okay rule. And now I'm going to change its name to, as long as you do it to all the pieces, it's okay rule. I want to get x in the middle, because once I have x in the middle, I'll know what the range, big to small, x needs to be. Now, in this question here, what would I do to the middle to get from x take away 3 to x? What would I do to this guy to get x? Any takers?
I'm gonna add 3.
You're going to add 3. I'll put a little baby add 3 there. But shouldn't I add 3 everybody then to keep everything balanced? That's what I mean by as long as you do it to all the bits. So this guy is 3.5, which is 7 halves. And this guy is 2.5, so that's what, 5 halves. So there we go, guys. It took a little bit more work, but we now have our interval of convergence. Do you notice that it's not quite as nice as the other intervals of convergence? You remember the earlier ones, isn't it the same 2 numbers, 1 plus and 1 minus? Do you notice that now the 2 numbers are quite different from each other? Right, 5 halves and 7 halves. Secondly, in this question here, it is possible for that to be -1/2 and that to be 17 halves, right? So the outsides, the intervals, are going to be different. That's just the way things are. Now, I need to find the radius of convergence. And you can get that essentially 2 different ways. The first one is visually. So imagine that you've got a number line where the x's are going to be put. The center was 3. And on one side, we had, what was that, be 3.5, which is this guy. And on the other side, we had 2.5, which is that guy. So this represents the values of x where our power series converges. And r is the distance from the center to the outside. So can you see the distance from here to here is a half, and the distance from here to here is a half? So r is a half. So far, so good. Now, if you do it visually, that's how you get r. Another way to get r. Take the biggest number in the interval, subtract the smallest number of the interval, and then half your answer. Yeah, that's a different way of getting it. So we have our initial phase 1 interval of convergence, and the r value is going to be a half, and that's not going to change. And now we need to test our endpoints. And one of them is 5 halves. We'll do that one first. And so it's going to be from n equals 0 to infinity, 2 to the n, x minus 3 to the n over n cubed. And we're going to plug 5 halves in here. So we have 2 to the n, 5 halves take away 3 to the n over n cubed. Five halves take away 1 is negative 1/2, so you're going to have negative 1/2 to the n. Typically, if you get a negative number in a fraction, or even just a fraction that's positive, you split it. And we split it as a negative 1 to the n over a 2 to the n. Can you see the cancel, which pretty much is guaranteed to happen? Something somewhere is going to cancel out somebody else. And all I'm left with is that guy over that guy. Okay, does this series converge or not? And tell me what test you would use to find out. What test would we use? We've used this test before in similar situations. What would you use? Any takers? There's your clue. Who uses negative 1 to the n? What kind of test works with things that have negative 1 to the n in it? Okay, it's an alternating series test. And can you trust me that eventually after 5 minutes, you'll be able to prove that it converges? Now, if you then go on and you test the other endpoint, which is 7 halves, you will eventually get, and again, you're just going to trust me on this, you eventually get that guy after a lot of work in cancelling. Okay, maybe we'll have more success on this one. What type of series is that? What test could I use? Because it's a pretty straightforward test. Who do you see here?
P series.
I agreed. And it's a P series where P equals 3. And since 3 is bigger than 1, would you agree it converges? So it looks like in this question, both endpoints converge. So the interval of convergence is 5 halves, 7 halves, and the radius of convergence is a half. And after all that hard work, that's all you write down in your homework, those two things. So when you are looking at, this endpoint here, right here, you're going to be saying to yourself, okay, divergence test, alternating series test, p-series test, limit comparison test, and God forbid you ever need to do an integral test. But you'll keep away from that integral unless nothing else, you know, seems to work. And you test it and you'll get convergence or not, depending on what the truth is. And you'll test it and you'll get convergence or not, depending on what the truth is. And that'll tell you what to do with these two endpoints. So let's pick one. And I'm picking this one because it's a special case. Special cases, sometimes good things. This is a version of question 7. Whenever you see an n factorial floating about, that is a good sign, because n factorials tend to generate two extreme situations. Either the answer is everybody, or it's nobody except 0. And the reason for that is that n factorial and n to the n for that matter are really powerful, right? They tend to do a lot of damage on the good side or a lot of benefit, or the bad side, a lot of benefit on the good side. So here goes. The limit as n tends to infinity using the ratio test. It's going to be the limit as n tends to infinity of x minus 10 to the n plus 1 over n plus 1 factorial. And then you multiply by the upside down version, but using n. And we got some cancelling. N factorial cancels with this guy and leaves n plus 1. X minus 10 to the n plus 1 cancels out x minus 10 to the n. And this time you get x minus 10 left over. So we're looking at the limit as n tends to infinity of essentially that guy and this guy. Basically that n plus 1, I had to give it a 1 so I could write it down. And in this case here, brute force works. It's 1 over infinity plus 1 times that guy. It's 1 over infinity times that guy. 1 over infinity is 0 times that guy, which means the limit is 0. And if the limit is 0, it's guaranteed to be less than 1, right? Which means it will converge. And not only will it converge, won't it converge for any value of x? It doesn't matter whether x is 2 billion or 22 trillion, right? And so the interval convergence is everybody, and the radius of convergence is infinity. Do you see why you want an n factorial in your question? Because the work tends to be much quicker, right? The conclusion is easier to do. If I had done this series with one major change, I put the n factorial on the top, right? If we went through that entire working, do you know we would prove that the limit was infinite and therefore it would never converge, right? Except when this guy is 0. So the difference would be interval convergence is nobody except x equals 10, right? You know, when you move the center, you move the only guy that works, right? When that was x to the n, x equals 0 is the only guy that works. Here it's 10. And so you would write it like that. Are we good? Any questions? Well, you're hanging in there, so that's a good sign. I'm just scanning through to see if there's anything particularly going on. Let's try this one. This is question 11. Right. See what the ratio test ends up giving us. N plus 1, x minus 6 to the n plus 1. Okay, the guy's already n plus 1. So if I turn this guy into n plus 1, I now get n plus 2. You comfortable with that? N plus 1 more. And then you turn me upside down and use n's. See what we get. These guys don't matter. Remember what I said? Negative ones just kill each other off. And if there's anything left, it's 1, so it still doesn't matter. This guy cancels with this and leaves me with an x minus 6. So I'm left with n over n plus 2 and an x minus 6. That n on the top, that n plus 2 on the bottom, and this guy goes here. Okay, we're going to do this one quick. What will the limit as n tends to infinity of that fraction n over n plus 2 be? And it's not a trick question. There should be one of you to do it, which was a clue, by the way. Which one of you is going to tell me that answer?
I have a question about the top line. Wouldn't that n be n plus 1?
Wouldn't that n up here? Oh, thank you. Natalie's on top of the game. Good answer. Good to catch that. The good news is the answer's the same. So, which one of you is going to tell me that answer? Now, John gets the joke, so he already knows the answer. Come on, help John out. Join with him. What's the answer? No? Okay, tell us, John.
It's 1.
It's 1. Can you do L'Hopital or divide top and bottom by n? Right? You know, there comes a point in time where you should just be able to look at something and say, I've done 100 of these. I don't even need to think about it. I know that's going to be that guy. So that's going to be 1 times this fella. And that's going to be equal to that. And we'll come back to that. Let's just focus on things that happen a lot and what the answers would be. Imagine you had that guy. What's the limit going to be? Well, if you cover up everybody, can you see it's 2 over 4, it's a half. That's how quick it should be. Now, I know the answer. To prove it, just do L'Hopital a couple of times or divide the top by n cubed. You know, the proving part is, once you know the answer, the proving part's straightforward. Suppose I got that. What would the answer be? There. What would the answer be now? Two over 4 gets you half.
Just be 4 over 3, right?
Yeah, 4 over 3. And then you can prove it by L'Hopital or whatever method, right? I'm skipping out the proof. Once you know the answer, you can fill in the proof, right? You know what you're going to get when you finish. Now, just to show you, there are other things that can happen. That answer is actually not 4, because you notice the top's only an n and the bottom's bigger, it's an n squared. It is a number, but it's not 4 and it's not a quarter, right? That guy, what number would you get? Now notice all you do is cover up everybody except the best term. What would that get you? What's chance? 0. In the big scheme of things, doesn't that cancel down to 4 over n? And 4 over infinity is 0. Now, if you turn it on its head, the other final combination could be that guy. Now, when you cover it up this time, do you see that the n square's on the top and the 4n is in the bottom? And when that happens, won't the answer be infinite? So these are the types of things that are very common, right? Happen to you and it happens a lot of times. And it's good if you can feel comfortable about looking at that guy and saying the answer is 1. Now, back to this question. We've just found the limit of the ratio. It has to be less than 1 to converge. And so I now have to solve for the interval of convergence. I need to find out what values of x this is true for. So we do that guy. And then you add 6 to both sides. And so my interval of convergence is from 5 to 7. And my radius of convergence, well, what is my radius of convergence this time? It's 1.
Is it 1?
Yeah, it's 1. I was just doing it in my head. 7 take away 5 and half it, right? So 2 take away 2 gets you 1. And at this point here, what we would then do is we would test the 2 endpoints. We would test 5, and then we would test 7. And I'm going to kind of cheat and tell you what you would eventually get. If you plugged 5 in here and did all the things that you needed to do and tidied it up, that's what you would end up with. Now, that guy is going to diverge. And I know it's going to diverge because I could do a limit comparison test using 1 over n. Limit comparison test. And that is a diverger, so this guy is going to diverge. Now, if I tried 7, can you trust me that you end up with this guy? And this guy has a -1 to the n in it, so I know I'm going to do the alternating series test. And once I finish the alternating series test, I'll find out that this one actually converges. Again, can you just trust me that that's what you get? So what we now would do is we'd go back to this interval and we'd say x equals 5, no good, stays put. But x equals 7, you can actually use it. So the new and final interval of convergence would be from 5 to 7, can't use 5, but you can use 7. And the radius convergence is still what it always was. Any questions about that?
It seems like the AST comes up a lot on these.
It does. If you ever see a -1 to the n, your best bet is go alternating series test, right? And if you don't see one, right, if it's not got any, then pick something else. But try and pick the easiest. So try and pick things like P series, alternating series test, maybe even the divergence test now and again when you're lucky. Because you could get sigma n squared, couldn't you? And that would be a divergence test. If you see -1 to the n, alternating series test and do what you need to do to find out if it converges or not. And if everything is positive, as it is here, use some other test, right? Limit comparison test is a pretty common one to use in a lot of these questions. Now, the more you do these, do you see you begin to say, okay, you're going to get a series and they, you know, they look like this, go alternating series test. And if they look like that guy, then, you know, pick a different test. We are getting pretty close to the end, so I want to show you another one that looks like the guy we just did, and then the last ones are extra special weird ones. I want to show you how you deal with those. So let's do one that's pretty much like the one we just did. This is a version of question 12. Right, that's an n. Okay, so the limit as n tends to infinity. Oh God, I got a joke. Got to tell you, came into my head. How much does a chimney cost, Calvin?
A couple grand.
No, it's totally free. In fact, it's on the house.
That was a good one.
That was a good one.
Okay. Came into my head, so you know me, if it comes in my head, I have to get rid of it. There we go. So we are going to be doing the limit as n tends to infinity. Okay, that guy is n plus 1. That guy is n plus 1. This guy is n plus 1. Then turn them upside down. Natalie, did you like that joke?
I did, but I don't see how this reminded you of it.
Oh, it didn't. There is nothing I did that reminded me of that. But you know, the way my brain works is just random thoughts come into my head, and that was a random joke that just came into my head. So the limit is n tends to infinity, right? Well, let's do some cancelling. Hasn't this thing happened quite a lot, right? 4 to the n and 4 to the n plus 1, right? They're pretty common. This one doesn't have it, but doesn't n plus 1 factorial cancelling with n factorial happen quite a lot, right? I've got a little bit of cancelling. Isn't x plus 2 to the n plus 1 going to kill this guy? And aren't you going to typically be left with just a single x plus 2, right? Typically. Right, let's see what we've got left then. I have an n plus 1. I have a 6n. And I have an x plus 2. Right? Comfortable with the bits that are left? N plus 1, 6n on the bottom, x plus 2 on the top. Right. What's that fraction going to be equal to? And it is a fraction. What's the answer? The limit is n tends to infinity of that guy. If it helps, there we go. Can you see it? N over 6n. What's that guy going to be? Any commenters? Anybody want to go for it?
And over 6n, wouldn't it be 1/6?
It is indeed. There you go. And n plus 1 over 6n is also going to be 1/6, right? And L'Hopital will do it for you. That's the proof part. Now, we know that the ratio test says whatever the limit is, it needs to be 1 to converge. And what I'm going to do is I'm going to take this guy and multiply both sides by 6. And I need it in this format, don't we? So that we can get the interval of convergence and all the other good stuff that comes from that. So I'm now going to solve the inequality, right? The usual way, right? That guy becomes him. What would I do to each piece to get the x on its own in the middle? Because that's kind of what we want. So what would I do to here, to here, and to here to get an x in the middle? How would you turn this fella into that guy? What would you do to him? Any thoughts?
You're gonna subtract 2.
You are. And don't you subtract 2 from everybody. And so what you end up with is that x is between -8 and 4. So our initial interval of convergence is -8 to 4. And the radius of convergence, I'm going to do the last guy, take away the first guy halved. And that's going to be 12 halved. And so the radius is 6, right? Cool. You could get that different ways, but I'm doing it that way. Now, all I need to do next is test the 2 endpoints. So I'm going to test x equals -8 first. And I'm plugging -8 in here. So -8 add 2 to the power of n over 6 to the n. -8 add 2 is -6 to the n over 6 to the n. Typically, if you see a negative like that, you split them into 2 pieces. So it's -1 to the n, 6 to the n over 6 to the n. And things being what they are, you always get some kind of cancelling. And I'm going to rewrite this guy that way around, because to me that looks more sensible. Right. Alternating series, the thing's increasing, it is divergent. Are you comfortable with that one diverges? If you think about it, isn't it -1 add 2, -3 add 4? It just goes weird. So alternating series test, you could also do divergence test if you wanted to. And if whatever one you use, you'll come to the same conclusion that it diverges. So that guy's not good. Can't use him. Oh, maybe we'll get better with the other one, which is what, 4? So it's going to be sigma n 4 plus 2 to the power of n over 6 to the n. Well, that's going to be n equals 1 to infinity. 4 plus 2 is 6 to the n, all over 6 to the n. Cancels. And you are left with n equals 1 to infinity of n. If you wrote that down, it's pretty obvious. It's 1 plus 2 plus 3 plus 4. It diverges. And the divergence test would be the one I would use. And we know it diverges. Which means you're no good. So there is your interval of convergence, and there is your radius of convergence. So when this guy was x, and now x plus 2, isn't it very similar process? It's not like we changed a lot, right? We did the same ratio test. It looked a little bit more work at the end, especially trying to find out the values of x from a guy that looks like this, but we got it. And testing the endpoints is pretty similar to what you would do in both situations. So I promised you a weird one, and weird one it is. So there is 2 of them. The first one is 13, or a version of 13. Well, what's weird about this guy? Look at the center. It's not x minus 2. It's 7x minus 2. Do you see that? And that's going to make a difference later on. Unless this is one of those questions where it doesn't matter who X is, it always converges, right? That could happen, right? But I doubt it's going to be the case in this one. So we're going to do the limit as n tends to infinity using the ratio test. Top guy. Make everybody n plus 1. Then turn them upside down. And use n's. Okay. There are a couple of things that can cancel here. Even although this 7x minus 2 looks weird, there's a 7x minus 2 here and there's another one here. And the only difference is that this is a n plus 1 power and this has got an n. So you're allowed to cancel them and you're going to leave a 7x minus 2 behind. And if I look over here, I have these two guys and they cancel and there's going to be a 7 left behind on the bottom. So I have an n and a 7 lots of n plus 1. And I have that guy. So we have a 7, an n plus 1, that's these two guys. And we have an n, that goes there. And we have this piece which we tag on at the end. Now, if you make or look at this limit, n over 7n plus 1, would you trust me that the limit of that one would be 1, 7? And you could prove it by dividing the top and bottom by n or doing L'Hopital. And if you need to see it a little bit clearer, call the bottom guy 7n plus 7. That might make it seem a little bit easier. But whatever way you do it, it's a 7. So that's what the limit is equal to as n tends to infinity. And according to the ratio test, it needs to be 1 to converge. It needs to be less than 1, I should say, to converge. Well, if you multiply both sides by 7, you get that. Are we good? Now, I'm going to do the exact same thing if that had said x minus 2. I'm going to solve this inequality. And the way you do it is that guy gets sandwiched between 7 and the negative of 7. Right? That's how we did all the others as well. And now I'm going to add 2 to both sides. And what do you think I'm going to do to all the sides to get x in the middle? So to get from here to here, I added 2 to everybody. What will I do to everybody to get 7x and turn it into just 1x? John, you thinking?
No, it's usually divided by 7, but
Yes, it is.
I just no,
You weren't comfortable or confident that it was 7.
no, I knew it was just. I was just wondering if anybody else was going to answer because
Oh, I hear you, John. Poor John gets all the hard work. You better, if you meet John, you better give him 2 coffees and a bottle of Guinness, right? Because he's the poor soul that gives everybody else a chance, and then if nobody does it, he'll chunk in. So we're in a team sport here, right? You can't let John score all the goals because then he gets big-headed, right? So Calvin, you're going to have to sneak over sometimes and take the ball off him, right? And chuck in an answer.
Yeah, I can do it.
Right? And Natalie, you've got the same job, right? You're going to show how clever you are compared to the other two by telling us the answer and before the other two even have a chance. So yeah, poor John's getting stuck with the job.
no,
Right.
I think like personally, I think they know. They just maybe don't want to answer. I don't know.
Ah, no, they get shy.
Well,
you know that.
maybe-
Yeah,
I
Maybe a little
insist on
bit.
giving John a shot every time.
Oh, no, Calvin. I think your nose is getting bigger there. You shouldn't worry about getting things wrong. Really, if you say to me, "Oh, you multiply by 7," and I say, "Well, do you really think that?" and then I might talk it through, because sometimes when you say something wrong, it gives me the opportunity to tell other people why it's wrong, and so they learn from it. So, telling me the wrong thing to do is just as good as telling me the right thing to do, right? So even if you are wrong, say this is what I think it would be based on what I believe is happening, and hopefully it's true. But if it's not, we have a chance to correct it. Now, in this world here, this interval convergence, I think the easiest and best way to figure out what the radius of convergence is just to take the first guy and subtract the second guy and half it. I think it would be just easier to do it as a calculation. So the radius of convergence is that guy, take away this guy, and then basically halved. So what's that? 9/7 add 5/7. God, why can't these numbers be nice? Oh, wait a minute. They are. Would you believe? It's 1. Unless I can't count, which is this time of night is likely, but it looks like it's 14/7, right? Which is 2, and half of 2 gets you 1. So the radius of convergence was actually nice. Now, what we're working with right now is that we've got that guy, and we know, or at least initial phase, is that for a starting point at least, there is the interval convergence, and we don't need to worry about the radius convergence. Once you know what it is, it's never going to change, which means that we have to test two different endpoints. Now, I'm getting a little bit of a time crunch here, so I'm going to cheat a little bit. I'll just do one of these and tell you what the other one is. So if you plug -5/7 into this series, let's see if that ends up being a convergent series. So it's going to be 7 times -5/7, take away 2 to the power of n over n times 7 to the n. I know it looks messy, but it's going to become a lot nicer shortly. Those two guys give you -5 take away 2 to the n. And those two guys get you -7 to the n over n 7 to the n. And we split those guys up into 2 pieces, as pretty much standard. And then, bingo, we are looking at this series. Right. I'm picking John. John, would you agree that's a classic alternating series?
Yes, sir.
Can you tell looking at it whether it's going to be convergent or not? If not, you would do the process and find out. But just looking at it, what's your gut feeling?
It converges.
And it does, right? So you would prove it, but it converges. An alternating series test, right? Now, if you then do the other endpoint, which is what, 9/7, can you trust me that you get that? Okay, put you in the spot today, Calvin. You ready? Do you recognize that guy?
Yes, I do.
And what is he? What'd you call him?
Well, really, I see 1 over n, but
Right.
yeah, it's a P.
It's a P-
Is it a P
that's
series?
That's what I'm asking you. It's a P
Okay.
series. And P equals 1 and it diverges.
Yeah.
You might have recognized it as a harmonic series, which also diverges because it's the same series, right?
Yeah.
Two names.
I was gonna
And that, mhm.
I was gonna say harmonic series, but I couldn't think of it. I kept thinking like harmonica, but I couldn't remember the word.
Right. And secondly, even if you couldn't put a name on it, you knew it diverged, which is kind of more important, right?
Yeah.
Because labels are just labels, right?
Yeah.
knowing what they do is more important than knowing what to call the thing, right? In a funny sort of a way, it doesn't even matter if you can't remember what the name of that test is, as long as you can do the test.
Yeah.
Right. Now, in this world, that guy converged, so square bracket, and that one didn't. So do you see the only little change was square bracket here, and we are done. And are we good? One more of these, and then I have some stuff I want to show you. This is 15, actually, the last question in the list. This fella, 4x plus 1 to the n over n squared. And it's the limit. It's another one of those where it's not an x, right? It's a 4x, a 2x, a 10x, right? That's what you're going to see, right? So it's very like this one. It's not x plus 1, it's 4x plus 1. So it's going to be the limit as n tends to infinity of an plus 1 over an. And that's going to be the limit as n tends to infinity of make everybody that's an n plus 1. And then turn the other guy upside down. There's really not a lot to cancel here. That guy cancels with this guy, and you're left with a 4x plus 1. That's pretty much all you can do. So what I'm now going to do is write down what's left. And on the top, there's an n squared. And this guy in the bottom, I'm going to call him n squared plus 2n plus 1. And then we have what? That guy. Natalie, you ready to get picked on?
Equals 1.
Ah, yes, you nailed it. If you want, you had to prove it. Couldn't you divide top and bottom by n squared, or couldn't you use L'Hopital? But you're right, it's 1. And so we are looking at that guy, and it's less than 1. Sorry, it has to be less than 1 according to the ratio test in order to converge. So from here, we now solve this basic inequality to find out what values for x that's true. Right? So this guy goes in the middle, 1 and -1. I'll then add 1 to both sides. And then I'll divide everybody by 4. Are we comfortable with that? Add 1. Add 1. God, I am getting tired. I made a mistake there. Shouldn't I have subtracted 1, not added 1? So subtract 1 from both sides. And then divide both sides by 4. There. Okay, I got it the right way around the second time. So we have an interval of convergence from -0.5 to 0. And R is what? 0, take away -0.5, all divided by 2. R ends up being a quarter. So to get from here to here, subtract 1 from everybody. To get from here to here, divide everybody by 4. So that's the correct interval of convergence, at least in phase 1. So we have to test our endpoints. So I'm going to test x equals -0.5. And the guy that we've got is n equals 1 to infinity, 4x plus 1 n squared. Now, if you plug in -0.5 here, let's see what you get. You get 4 times -0.5, add 1 to the power of n, all over n squared. That guy is -2, add 1 to the power of n, over n squared. That guy is -1 to the n, over n squared. Anybody, Josh and Tom and anybody else who's here, you want to tell me what test I should use for this series? It has a feature that kind of screams out, use me. What test should I use? And it looks like we may have typed an answer. And you are correct. So Thomas said alternating series test. And can you trust me that it converges? You know, eventually you'll prove that. Now, if you, and I'm cutting a whole load of corners here, but if you do x equals 0, and you do the same kind of working, that's what the answer to the series would look like. Calvin, do you recognize 1 over n squared?
Not as much as 1 over n, but I can try.
Okay, it's a p series.
Yep.
What's the p value?
P-value, I want to say, would it still be 1 or would it be, would it be a half?
Oh, no, but you're close. It's 2. It's whatever the power
Yeah.
of n is. Right?
Okay.
So if it's sigma 1 over n cubed, it's 3. If it's sigma 1 over n to the 4, it's 4.
Yep.
And if it's sigma over the square root of n, then you have to go into fractions, you get half. And since 2 is bigger than 1, that means it converges. So in this last question, and then I want to show you some stuff on Canvas, the interval of convergence, the 2 endpoints are also usable. And so it's square brackets, negative infinity and 0. And when you do WebAssign answers, that's essentially all you write into one of the boxes, and that guy's the guy you put in the second box. But it will ding you. If it's curved, it has to be curved, and if it's square, it has to be square. Secondly, it doesn't even give you a clue. Couldn't you be 90% right and just got one of the brackets wrong? It just says you're wrong. So you got to be careful, like that mistake I did there, right? It wouldn't matter what I did. If I used the numbers I had a few moments ago, I'm always going to be wrong because my interval was wrong to start with. So you have to just be careful. And to finish with,